Hello, this is the start of the calculation portion of the deliverable. If you look in Canvas, you will find an attached document that looks very similar to this one with all three problems that you have to solve. Now, I did change some of the numbers for when I walk through this tutorial, so that way you can't just copy my work. So please go through the same exact steps that I'm doing with the numbers actually given in the problem. And a lot of these are based off of design components of our semester project. For example, you might look at this first problem and see a 40 by 70 foot concrete slab. And that is, also the requirement that we had for the project. So we're trying to make some of these calculations pretty relevant to what you did for your design work, but all of these problems should look the same for all of you. So with that being said, you are more than welcome to work with each other. You shouldn't just be copying each other's work though. Every single person is required to submit their own work. If we see two people that submit the same document, well, just don't do that. It won't go down well. And also, if you work with anybody, please just on the top of your document write who you worked with. And that way we can keep track of, who has the same work, who doesn't. And these three problems are really just designed to get you introduced to some geotechnical concepts and really a lot of structural concepts as well. And I will walk through all of these with you. So this is all going to be pretty much entirely new to you, and that's okay. I'll walk through the whole problem with you. You're more than welcome to go to office hours or ask questions on Piazza. But the steps that I do are the steps you can do just with slightly different numbers. This first problem that we're going to go over in this video has to do with soil strength and the weight of a concrete pad. The second problem here is a load path problem for a roof system. You will recall in class that you talked a little bit about load combinations, and that's something that we're going to get into in this problem, as well as tributary areas. And this third problem has to do with a retaining wall and calculating its overturning moment. So that's something that we will walk through together. Now, I want to make a note as we start this first problem. This is by far probably the most sort of contrived problem. Geotechnical engineering is complicated and structural engineering is also complicated. We are going to calculate the soil bearing capacity in this problem, and it's sort of actually a fake soil bearing capacity. This is not going to be the real soil bearing capacity, but calculating the real soil bearing capacity requires a lot more knowledge and a lot more calculations than we have time to cover. You are all going to take geotechnical engineering if you haven't already. So know that this is going to be sort of fake, but we'll walk through it together anyways. It still has some meaning to it, and hopefully you'll learn a thing or two as we do. So you can see here we're looking at our concrete slab, the 40 feet by 70 feet, and we have a plan view right here and a sort of profile view of sorts on these two images. We have our dimensions for our slab, and our slab actually has two layers to it. We have the actual concrete itself, which is, if we go over here, 4 inches deep. And then we also have a cement finish on the top. This is pretty common to have, and that is 1 inch deep. Depending on the building and like the architecture and how much money they decide to spend, this cement finish could be cement finish. It could be some kind of terrazzo or tiling. That's pretty common. So these can be different materials, or there can even be multiple layers depending on the need. But here we have 2 layers. We're also given in the problem that below the concrete is 4.5 feet of clay. Now check your numbers. I think you guys will have 4 feet here and probably 130 pounds per cubic foot as the weight. So keep that in mind. Don't copy my numbers, just copy my process. So that's what we're given. This depth. This is the weight of the clay, basically, is a way you can think about this. So how much it weighs per cubic foot. Then you can see here we have some of our other weights. So we have the weight of concrete. Weight of concrete is very standard. 150 pounds per cubic foot is sort of your base assumption. And then as your concrete mix changes, whether you add more water, more gravel, more sand, or cement, that number will fluctuate up and down. We also have the cement finish given as a pound per square foot. So that would be a stress, right? Pound per foot squared. And we're also given the weight of the assembly area. So our concrete pad is an outdoor pavilion. At least for me, I have it as an open space. It could be enclosed for you, but regardless, it's a place where people should congregate. And so this is taken from, I believe there is a slide in the lecture deck that shows this, but this is part of the ASCE design guidelines. This is essentially saying if you have an area that acts like an assembly area, you should expect a live load of 94 pounds per square foot. Now, again, you'll have different numbers here. I think you might have 100, I think you might have 30, or something like that. So use the numbers that you're given in the document attached on Canvas. But this is just saying that, if you have people on this concrete slab, you can expect an additional 94, 100, whatever the number is, pounds per square foot of load on your slab, like this. Now, the problem is asking, is the soil bearing capacity high enough for the concrete slab? Just to reiterate, we're not actually going to be calculating the real soil bearing capacity. That's a little bit more complicated. Instead, we'll be using essentially the stress of the soil as a proxy for the strength of the soil. In reality, what we're calculating is the amount of pressure the soil is going to exert on whatever layers below this. So say you had a bedrock foundation or you had a layer of sand here. We're basically going to calculate the weight and the pressure from the concrete slab and then the weight and the pressure from the clay. And then all of that's going to be down on this foundation. For the purposes of this exercise, we are essentially going to compare the two, though. So we're going to see if the weight of, or the stress, sorry, of the clay is the stress of the clay, right? Because this is, the stress is going to be kind of acting in all directions. Is the stress of the clay greater than or less than the strength of the concrete pad, the stress of the concrete pad? So we're going to be doing a simple comparison like that. This isn't what you would actually do, but it gives you some introduction into both structural and geotechnical engineering. So our governing design equation that we need to be working with is seeing if the clay stress is greater than or less than the slab stress, right? The amount of pressure that is being exerted. And ideally what we want is the slab stress to be lower than the stress of the clay, or in this case, we're just going to say the bearing capacity, right? The strength of the clay. Again, just to proxy. If the slab has a higher stress or a higher pressure that it exerts on the soil than the soil can take, then that's going to lead to settlement and deformation. Our concrete pad is going to push into the soil, and that would be really bad for our flat slab. But if the ground strength, the clay strength is higher, then we'll say that the concrete pad will just rest on top, and that is good. So that's what we're looking for here. So our equation here is pretty much the unit weight of the slab needs to be less than or equal to the allowable stress or the bearing capacity of the clay. Now, we also want to keep in mind that we don't want these numbers to be close, right? If the weight of the slab is just, a couple of pounds underneath the clay, that is really close to, our failure condition. So, and this is very common to do for structural engineering and geotechnical engineering. We add basically a factor of safety. And that factor of safety can be applied either or in addition to, this is our load and this is our strength, right? So we could either double the load, or in this case, we're halving the strength. And there's a lot of deep engineering analysis that goes into, these factors. For the purposes of this problem, like I said, it's a little bit contrived. So we're just going to go with half the strength of the clay should still be able to hold up the slab. So we need to essentially find both of these numbers, right? And we can start with the slab. This is going back to your structural engineering lecture. We have two dead loads that were given right here, dead load 1 and dead load 2, and then we're given one live load here. We're also given two load combinations that we have to test for. So this is a way of combining different types of loads, and this is another method of implementing a factor of safety. We're taking whatever loads we're expecting and multiplying them by constants and combining them together to get our total load that we're designing for. So let's start by finding all of our dead loads. So we have two dead loads. We have the concrete and the cement finish. Our concrete is 150 pounds per cubic foot, and the cement finish is in pounds per square foot. So we need some way of getting these to be in similar units. And we can do that by multiplying out one dimension, right? If we have length times width times height here, if we multiply by some dimension, then we can make that turn into feet squared. So the depth of the concrete, it would be the easiest one to do. So we can multiply by 4 inches here, and that will get this to be in a pounds per square foot as well. So I might multiply this by 4 inches, and I'm dividing that by 12 inches so that this way it represents a foot. We're in common units then. Then from here, I can add the 1 inch. This weight is already given as 1 inch of 31 pounds per square foot. And we have a 1 inch depth, so we don't have to do anything there. We can just add the 31. Now, again, your numbers are going to be slightly different than mine, and I actually haven't solved the problems with these numbers, so I will be putting them in a calculator as we go. So you might be looking at this video and thinking that it's long. I apologize, but I am walking through the problem with you, so it should not take you significantly longer than it takes me. All right, so that's our total dead load. Our live load is much easier since we only have one number. We don't have to do anything with it as long as it's in pounds per square foot, which it already is. So our live load is simply just 94 pounds per square foot. For you, it will most likely be 100. Now we need to combine these. So we need to test out our two different load combinations that we have here, right? And figure out which one is our design load. So we want to design for whichever one is the highest, right? Because that's the worst case scenario. So we're going to calculate both of these numbers and pick whichever one is higher. So all we have to do here is plug in our numbers. So here we have 81 pounds per square foot. And remember, pounds per square foot, that's the same thing as force per area. So this is a stress. And this doesn't even take a whole lot of math to look at, but we can pretty clearly tell that our bottom combination with the live load is going to be greater. Still need to calculate both numbers though. All right, so these are our two numbers from our load combinations. And here we can see which one is clearly greater. So we will be using this one. So that is one side of this equation figured out, right? We also need to figure out the other side of the equation, and it would be really great if we can do it in a pound per square foot manner. That way we can directly compare these numbers, right? We care about the amount of weight going into any kind of unit of this on our soil. We don't really care about how big the slab is necessarily. That 70 feet and that 40 feet don't make as big of a difference, because if it fails in any one point, then that is a problem. So now to calculate the clay portion of this, we know our clay has a specific weight of 130 pounds per cubic foot, and this is pretty much just the density. We also know how deep our clay goes. For me, it goes 4.5 feet deep. For you, that will likely be 4. So again, I can get this in a pounds per square foot here. Sorry, 4.5 for me. So there is our number here. Now that we have both the strength of the clay, again, this is strength in big quotations with a bunch of asterisks. Don't go to Professor Burden, who teaches geotechnical engineering, and say that this is right. I know it's not, but we're just doing this for learning purposes. So we have our clay strength and we have our slab weight. And now we can compare the two using this formula. So plugging our numbers in, we have 247.6 pounds per square foot. Needs to be less than or equal to 0.5 times 585 pounds per square foot. If I do that out really quickly, we get 247.6 pounds per square foot is less than or equal to 292.5 pounds per square foot. All right, so you need to show all of your work for the problem, similar to the way I just did. So show your work, and once you get to an answer, you need to box your answer. So I can box this, for example, and write just one sentence about what this means. So, for example, I can write here, our soil bearing capacity is greater than the weight of the concrete slab. Therefore, design passes. So there's a little bit of interpretation that you need to do here. For example, if your clay strength is less than your concrete slab, you might need to say something along the lines of, the soil might fail or deform or move under the concrete slab. Concrete slab could break, or like this is a safety hazard. What if the numbers are close? That's up to you to figure out. Does that mean you should somehow reduce the weight? Does that mean you should increase your soil strength? Just some things for you to think about, but just follow the same steps, show all your work, box your final answer, write down who you're working with if you do, and you have just 2 more problems to go.